So, hello everyone. Today we are going to start the second lecture of module 7 and we will be discussing mostly on fed batch and continuous operation today. So, in the last lecture we discussed batch operation, and in the batch operation we discussed two modes, with batch operation with cell culture and batch operation with enzymes. So, today first we will be starting with the fed batch operation. As you know, the fed batch is intermediate between batch and continuous culture, and then we will go with the continuous operation. Today we will be discussing continuous operation with free cells. So, fed batch operation, as I told, there is a inlet stream, but there is no outlet stream is not there. So, this is hybrid between batch and continuous mode, and nutrient feed added, it may be intermittently or continuously, and there is no outlet till the completion of fermentation process. So, mostly it controls the substrate level inhibition, because whenever there is a inhibition because of high concentration of substrate, then we can devise the feeding strategy in such a way that substrates are effectively utilized. So, mostly if you see in the fed batch culture, so it is operated with cells. It is very rare that fed batch is operated using enzymes. So, for fed batch operations we will be discussing with the cells, but before we go ahead, let us discuss further that why to go about the fed batch operation, what are the key advantages of this fed batch system. So, first is, as we discussed, to avoid substrate inhibition, particularly when substrate concentration is high at the inlet, it causes the inhibition. So, if you feed the substrate intermittently, we are able to tackle the most important substrate inhibition part. And second, it leads to the generation of high cell density, because by tuning the feeding rate, it is possible to extend both exponential phase as well as the growth phase. And this is further very important thing, that in presence of excess substrate, there may be formation of other byproduct, which say these undesired metabolites. For example, acetic acid is produced at high concentration of glucose. So, that also can be controlled, because the other metabolic pathway will not get initiated as long as substrate concentration is under control. Third is to control the oxygen demand, particularly for the production of Becker yeast, that is aerobic culture. So, in this case it is a growth associated product. So, the biomass production is directly related with the substrate concentration. So, if we can control the substrate, we are able to indirectly control the oxygen requirement. Next is this, to slow feeding of glucose in penicillin fermentation by Penicillium chrysogenum. This avoids the catabolic repression, or you can say it suppresses the undesired pathway. So, we can minimize the catabolic repression, we can control the substrate concentration, at the same time we should be able to achieve the high cell density and product titer. So, here for this case fed batch, as I told earlier, that fed batch with enzymes are quite rare. So, we directly discuss fed batch with free cells. Now, when we are discussing the fed batch, so there will be two possibility. One possibility is fixed volume fed batch, other is the variable volume fed batch. So, of course, we are adding the feed stream, but if you feed the very high concentrated feed, then you are able to add very small volume. So, it can be considered as a fixed volume, but if you are feeding a significant higher flow rate, a higher volume, then it becomes the variable volume. It means with time volume increases. So, for variable volume, let us say Vt will be your initial volume was V naught, flow rate is F and time t. So, this will become total volume Vt as V naught initial volume plus flow rate into time. Now, when we do this overall mass balance, so it says d rho V upon dt is equal to F into rho I. Rho I means density of inlet and rho is the density of the culture. So, typically in the fermentation we deal with dilute media. So, we assume this rho I equals rho. So, rho we are considering constant, we are assuming constant. So, it becomes dV upon dt is F. The flow rate is defined as dV upon dt. Now, let us go for mass balance for biomass. So, mass rate in, what is biomass in? F into xi, mass rate of generation, biomass generation Rx into V, mass going out 0, mass of biomass utilized 0 and rate of accumulation dxV upon dt. So, we are getting dxV upon dt equals Fxi and rate we are considering Rx, we are considering Rx is equal to mu minus Kd death rate into x. So, it is coming here. Now, this term particularly as we are seeing, it can be fixed volume, variable volume. So, volume we are not considering constant here. So, once we differentiate this, we will getting x into dV upon dt plus V into dx upon dt. So, what we will do, dV upon dt will term as F as we discussed here. So, this term will write F here, F into x plus V into dx upon dt equals Fxi plus mu minus Kd x into V. So, if you further rearrange it, so we typically will be rearranging in terms of d is dilution rate defined as F upon V. So, what we can do, we can divide this F and V. So, V will be cancelled out. So, we will go to next slide. So, it is here. So, what we are going to do, we are going to divide with V. So, this becomes F upon V xi, then this becomes mu minus Kd x and this becomes F upon V into x and F upon V will be dilution rate. So, it comes out to be dx upon dt as dxi mu minus Kd minus d into x. Let us assume negligible value of Kd. So, it becomes mu minus d into x and further if you are feeding sterile feed means xi equals 0. So, this term is 0, Kd is 0. So, this becomes dx upon dt mu minus d into x. Further, we will be seeing that this fed batch is operated at a high biomass concentration. So, typically dx upon dt can be considered constant and that we will be calling as quasi steady state. Let us next do this mass balance for substrate. The same we will be doing mass of substrate in F into SI, mass of substrate generation 0, mass going out 0, and the rate of substrate utilization R s into V plus rate of accumulation. So, we will end up with dSV upon dt is equal to F SI minus R s into V, and if you remember what is the rate of substrate utilization R s is, we are saying it is being utilized for the biomass, it becomes mu upon y x upon s. It is also going for the product formations, it is q p upon y p by s, and some part of substrate is utilized for the maintenance m s into x. So, in place of R s we are going to write this R s term and d s v upon d t. Again the same thing we have to do, we have to differentiate it. So, we will getting s into f plus v into d s upon d t equals f s I minus this term. So, this becomes d s upon d t as d, f upon v is d, s I, this s will come this side, the s I minus s minus the R s term, see v is cancelled out here. Now, this if now you remember, this is the equation 1 for the biomass we derive and equation 2 we derived for the substrate. So, what we are seeing here, biomass concentration is high, so that we are assuming dx upon dt as 0 at quasi steady state as I told. Similarly, what we are assuming is SI, substrate concentration is much higher than the S. So, the ds upon dt will also be considered as 0. So, first let us go for the biomass. If you put dx upon dt equals 0, then it becomes mu equals d. And what is mu? Mu is defined as mu max s upon k s plus s. So, if I just simply rearrange it, so it says d equals mu max s upon k s plus s, and if I will rearrange, you will get s as d into k s divided by mu max minus d. So, in this way we calculate the substrate concentration. Now, let us go to this ds upon dt now. So, ds upon dt is dsi upon s, and for time being let us assume maintenance, let us neglect maintenance coefficient and this product formation part. So, we are getting this equation ds upon dt equals dsi minus s upon 1 y of x upon s into mu x. Now, here if we assume this quasi steady state, ds upon dt becomes 0 and si value is much higher than the s. So, we will end up with d si minus s equals 1 upon y x upon s mu into x. Now, further as you know, we say this mu equals to d. So, this can be cancelled out, if this term goes to 0. So, we are getting x as y x upon s into si at quasi steady state. Now, similar to the biomass, the product formation is also written in the same way, P as y p upon s into si. Now, as we have discussed, in the case of fed batch, although we are assuming the x is constant, but as volume will increase, so total amount of biomass will increase because volume is increasing. So, we said B equals x into V. So, if we write dB upon dt, so it becomes x into dV upon dt plus V into dx upon dt. And what was the value of x, if you remember, that was y xs into Si. The value of x was y xs into Si. So, if you write dB upon dt as x into dV upon dt plus V into dx upon dt, and this was your x and this is your feed rate or the flow rate. So, it is coming particularly because here x into dV upon dt is f and x is coming, and for time being dx upon dt we are assuming as 0. So, we are getting dB upon dt as y x upon s Si into f, and now if we integrate quickly, so we will get B as B naught plus y x upon s Si f into t, and this t we will say t fed batch. So, in this way we can calculate at a given time interval what is the total biomass in a bioreactor. Now, we can see the profile of mu x and s for both the cases. Variable volume means volume is increasing, and fixed volume remains constant. So, in the case of variable volume fed batch, so we are assuming in such a way that the profile of S naught x and s they remains constant, and value of mu is decreasing slightly. Further, if you just see here in the case of fixed volume, the substrate concentration is declining here and biomass x is increasing here, and similarly mu is specific growth rate is slowly declining because the substrate is depleting here. These are the two profiles for variable volume fed batch and fixed volume fed batch. So, it has certain utility, this because particularly for when you are going for high biomass production, particularly Baker's yeast, because yeast biomass itself is a product. We can go with the fed batch operation, penicillin fermentation, monoclonal antibody for fusion, the production of single cell protein and enzyme manufacture, and ethanol manufacture is done using all three methods: batch, fed batch as well as continuous. But fed batch is also done where the substrate is intermittently added to enhance the operation time. Now, we will do one example here. So, it says Nicotina tabacum cells are cultured to high density for producing polysaccharide gum. So, here a stirred tank reactor was used. The volume of media is 100 liter. Maximum specific growth rate is 0.18. So, it says mu max is 0.18 day inverse and volume is 100 liter. Yield of biomass Y x upon S is 0.5. The concentration of growth limiting substrate is Si is 3%. 3% means it will be 30 gram per liter. The reactor is inoculated with 1.5 gram per liter of cell. The Xi is 1.5 gram per liter and it is operated in batch mode until substrate is exhausted. So, first it is operated in the batch mode and once the substrate this becomes 0, then media flow started again at a rate of 4 liter. So, for the fed batch the flow rate is 4 liter per day and we are assuming this quasi steady state condition. So, first question is related to the batch. You calculate the batch culture time and final biomass concentration. So, final biomass concentration we can quickly calculate because Y yield is given. So, it says Y x upon S is xf minus xi divided by Si minus S. So, final S we are assuming 0. So, it directly gives the xf and xf value you will be getting as 16.5 gram per liter. Now, next question is you calculate the batch time. So, for calculating the batch time, if you remember the equation TB for batch is 1 upon mu max ln 1 plus y x upon s divided by x naught S naught minus SF. So, all the parameters are given here. If you put this value, you will get batch time as 13.32 day. Now, if you go to part B, what does part B says? Part B says fed batch operation is carried out for 40 days. Then you say T fed batch is 40 days. You have to calculate final biomass. What is final biomass? If you remember, B equals B naught plus Y x upon S Si F into T fed batch. What will be the B naught? B naught will be B is, this is part B, B naught is x into V. What was the value of x we got? 16.5, volume is 100. So, it says 1650 gram. And if you put the value of y x upon s is 0.5, Si is, what is the Si? Feed rate will be the same 30 gram per liter, flow rate is 4 liter per day, TFB is 40 days. If I put this value, you will get B as 4050 gram. It means 4.05 kg, 4.05 kg. Now, we will see one more example for the fed batch. So, it says for the manufacture of Swiss cheese, Lactobacillus casei is cultivated under anaerobic condition as a starter culture. The culture produces lactic acid as byproduct of energy metabolism. The organism have following characteristics. The y-x upon s is 0.23, Ks is 0.15 kg per meter cube, mu max is 0.35 hour inverse, and ms is 0.135 kg per kg into hour. The reactor is operated in fed batch mode at quasi steady state with the feed rate of 4 meter cube per hour. So, it says F is 4 meter cube per hour and a substrate concentration of 80 Si is 80 kg per meter cube. After 6 hours, the liquid volume is 40 meter cube. So, it says what was the initial volume. So, if you remember in the fed batch, it says V T equals V naught plus F into T. So, what is the value of V T is 40, V T value is 40 equals V naught, we have to find out, flow rate is 4, time is 6 hours, that is it. So, initial volume will be 16 meter cube. So, the part A, the initial volume will be 16 meter cube. Now, next is what is the concentration of substrate at steady state. So, to find the value of substrate at steady state, if you remember the equation, part B is AS equals D into Ks divided by mu max minus D. Now, what is D? We have to find the value of D. D is F upon V, it is the flow rate 4, volume is 40 meter cube, 4 upon 40, it becomes 0.1 hour inverse. So, D is known, Ks is given here 0.15, mu max is 0.35, D is 0.1. So, we will get the value of S as 0.06 kg per meter cube, 0.06 kg per meter cube. So, initial SF, initial SI was 80, now it has become 0.06 kg per meter cube inside the bioreactor. Now, third is what is the cell mass concentration at quasi steady state. So, it says if you have to find the value of x. So, for part C, if you remember the substrate balance, it says D Si minus S equals mu upon Yx upon S plus Qp upon Yp upon S Ms into x. So, we need to find the value of x here. D is given to us, Si is known, S is known. Here mu will be replaced by D, mu equals to D quasi steady state, and Ms is given. So, we can ignore this term, we can neglect this term for time being. So, we will get the x as D Si minus S divided by, you can say D y x upon S plus Ms, and you will get value of x as 14.04 kg per meter cube. Now, further we will move to the next section, that is the continuous operation having this free cells. The first further in the continuous it is possible to go with this immobilized cells, enzymes and immobilized enzymes. So, there are different combination with CSTR that we will be discussing in the next lecture, but today we will be discussing this continuous operation with free cells. So, continuous means we assume the steady state flow, steady inflow and outflow of reactant and product. Constant reactor volume is constant because there is no accumulation, and we are assuming ideal mixing, uniform composition throughout the bioreactor, and catalyst, it may be the cell or enzyme, they can be free or immobilized, and the common application for CSTR in the brewing industry, wastewater treatment and yeast production. So, what are the key feature here? This we are assuming continuous stirred tank bioreactor, we are assuming homogeneous mixture of substrate, cell and product, and we are having controlled inflow and outflow to ensure steady state. These are the key feature of continuous operation. Now, we will do the same exercise. First, we will do the mass balance with the for biomass. So, you just see this is the inlet in, this is the out. So, mass in is F into Xi, generation rate of generation is Rx into V, mass going out is F into X, utilized there is no utilization of biomass plus rate of accumulation, as we are assuming steady state, the rate of accumulation term will be 0. So, we will end up with F Xi minus Fx equals, other you can see this Rxv equals Fx minus Fxi, and when we are feeding the sterile feed, then Xi is 0. So, this, so it becomes Rxv equals F into X, and F upon V is D. So, it says Rx becomes D into X, and what is the Rx? Is the mu into X is equal to D into X, then cancelled out X. So, it says mu equals D, that is the steady state operation in continuous culture, and further as you know D equals mu, and mu equals mu max S upon Ks plus S. So, if you can rearrange this, so you get S as D into Ks divided by mu max minus D. So, dilution rate we already know. In addition, there is one more term, that is called average residence time, that is 1 upon D. Tau is 1 upon D, then this will be V upon F, that is it. So, there are two terms, dilution rate and residence time. Next, we will do the mass balance for the substrate. So, rate of substrate in F into Si, rate of generation, there is no generation of substrate 0, going out F into S, then this term is not there, then rate of substrate consumption Rs into V plus rate of accumulation, at it is steady state, rate of accumulation is 0. So, we are ending up here this F Si minus Fs equals Rs into V, And what is the RS? RS will remain same what we discussed earlier. RS will be being utilized for the biomass mu upon y x upon s plus for the product Qp upon y p by s plus maintenance into x. This is the RS into V. So, further we can just divide f upon V as d. So, we are getting this f Si minus S, you can divide by V, it becomes d Si minus S equals mu upon y x upon S plus q p upon y p upon S plus m s this into x. So, from here we can find what will be the concentration x here. So, this was the mass balance for substrate. So, here we can assume this, we can neglect this two term product as well as this maintenance term. So, we will see, we will get x as d Si minus S divided by d y x upon S plus ms. Ms can also be neglected. So, we will end up d will be cancelled out, then we will end up x as y x upon S divided by Si minus S. So, this is exactly the same definition of the yield. What is yield? Y x upon x is delta x upon delta S. And this we have already derived S as dk based on the monad equation. So, this S can be replaced here. So, this becomes x as y x upon S Si minus S will be replaced by d k s, because S may not be known to us, but we know what is the Si, we do not know what is the S, but we know what is d, what is k s, what is mu max minus d. So, based on that we can calculate the value of biomass concentration. Similar mass balance we can do for the product. So, product in typically it is 0, but we will be writing F into Pi plus rate of generation Rp into V, going out F into P, utilization 0 and at steady state rate of accumulation is 0. So, we are ending as this P equals Pi plus Rp V upon x. And what is Rp? Rp equals to Qp into x, if you remember. So, Rp rate of product formation is specific product formation rate into x. So, Qpx into V. So, we are ending up P as Pi plus Qp x upon d. Now, here this is the equation for the biomass and this is the equation for the substrate. Now, if we just see the profile of both x and s, how it vary with the dilution rate. So, as long as low value of d, we are seeing nearly the constant value of substrate in the bioreactor, and if this is the case, if S is 0, then x becomes also constant, x becomes, if we just see, if you put S as 0, x become y x s into Si, just see x is also constant. But further, when this d reaches close to the mu max, then all of a sudden x becomes 0, and once x is 0, then this sudden increase rise in the S value, and S becomes S equal to Si, and this dilution rate is known as the D critical. We can say this is also the washout condition, the situation at high dilution rate where x reduces to 0. So, what will be the D critical here? In this equation, if you put x as 0, if you put x as 0, and D will be replaced by D critical. So, it becomes D critical into Ks divided by mu max minus D critical equals Si, and if I rearrange it, so we will get D critical as mu max Si divided by Ks plus Si, that is it. So, this is the D critical, we can always calculate. So, CSTR is operated at mu is less than D critical value. Further, we can calculate both volumetric productivity of cell as well as for the product. Qx is Fx minus Fxi divided by B, it becomes Xi is 0. So, it becomes Fx upon V or D into x. Now, what is x? We have discussed in the last slide. S is Si minus dk upon mu max minus k into Yx upon S. Similarly, we can calculate volumetric rate of product formation Qp as Fp minus Fpi divided by B V, and Pi is 0 because at inlet there is no product, it becomes D into P, that is the volumetric rate of product formation. Now, one more interesting term comes, then how to find the optimum value of D. So, what should be the optimum value of D? It should be the optimum value of rather X biomass, right. So, you just see, you can say volumetric productivity is given as D Si minus dk mu max minus D into Ix upon S. If you want to find the maxima, you have to do D Qx upon Dd as 0, and if I differentiate it and put at 0, we will get D optima as mu max 1 minus under root Ks. So, we are getting D optimum as mu max 1 minus under root Ks divided by Ks plus Si. Now, you just see this is the D optimum and this is the D critical. So, one need to be very careful that because D optima is very close to the washout. So, will this I will stop here, and in the next lecture we will see the chemostat with immobilized cells, chemostat with enzyme, then further chemostat with the cell recycle and cascade chemostat, followed by that they will briefly discuss this plug flow bioreactor. Thank you so much.